All right, good morning. Let's start. Do you have any questions before we start? Okay. So last time, we were at chapter 11, confidence intervals. And we'll denote that as CIs. And so general ideas. So general ideas about confidence intervals goes as follows. So suppose we have, right, IID sample from a population distribution that depends on theta. And theta, of course, is unknown. And so we discussed how if we just come up with a estimator, okay? If we have theta hat as an estimator for theta, then it's really good, all right? It can be used, but from some point of view, you may say that it gives no room for error because probability that theta hat exactly equals to theta is equal to 0. Okay. Let's say if the population distribution is continuous. Even if it's discrete, the probability that your theta hat, is exactly equal to the true value theta is really small. Okay. So in other words, it gives no room for error. Of course, this is not the fault of the estimator itself, right? It's just the methodology provides you with one single point. So right, that's why it's called a point estimator. A point, by definition, does not have any kind of fluctuation, does not have any room, right, for you to kind of move around. And so what we want, right, we want an interval estimator. We want a confidence interval. Okay, so the confidence interval conceptually will be two estimators, two statistics together, right? So this, broadly speaking, can be thought of as two stats. Of course, they're kind of closely related, but for now, let's just think of them as two stats, such that the probability, right, that your true parameter belonging to this interval, right, will be 1 minus alpha. It could be greater equal to or approximately. They all work, but I mean, in the ideal case, it's equal, right? So alpha here, right, or 1 minus alpha is the confidence level, right, of the confidence interval. Or I don't know, sometimes people refer to it as alpha, okay? But I think probably 1 minus alpha is 1 minus alpha is more appropriate because you say 95%, 99%, or 90% confidence interval, right? So typical alpha will be 0.1, 0.05, 0.01, right? Typical values, but all right. So what do we want to say here? So maybe first let's just take something out of, well, maybe let me look at an example. Okay, an example would be x1 up to xn IID normal mu sigma square. And we're going to do something a little bit strange in the sense that we will assume that sigma square assume known. Is really a traditional thing to do, probably for pedagogical purposes, like to expose the students to easy setup before, right, we do the more complex approach. But of course, right, sigma assume known is highly unpractical because population parameters are usually not known altogether. All right, but here, like again, it's assumed known just to make it easy to demonstrate ideas. All right, then we claim that a 95 or the 1 minus alpha, a 1 minus alpha confidence interval for mu would be x bar plus minus z alpha over 2 sigma over root n. Okay. So here, I guess z, right, alpha over 2 or z alpha is, I guess not the z score, probably is the z quantile, z, the normal, the standard normal. Alpha upper quantile. I mean, that's just a bunch of name. What it really means is a number, okay? Such that probability of the standard normal being above it is exactly alpha. Okay, so if this were the standard normal density, then if you have z alpha here, then the probability under the curve here is exactly alpha. So one thing to remember, right? So this is actually universal notation. It's universal notation. For example, we can have, you will see we can have a chi-square n alpha. We can have a t n alpha, and we can have z alpha. We can have f, sorry, little f, and 2 alpha. These are all upper quantiles, upper alpha quantiles of the corresponding distributions. Okay, so in other words, I think you have seen chi-square, you have seen z, right, normal. We haven't discussed t and f, but just think of them as some distribution that you can look up in the book. Basically, right, that this is a number such that the t distribution with n degrees of freedom, right, the probability that that distribution is bigger than that single number is alpha, right, and so on and so forth for the f distribution, the standard normal, and the chi-square with n degrees of freedom. The point is, right, that these are known numbers, they are known values. And you can look them up, right? In tables. That's when I went to school, right? That's all we do. Well, we look up things in tables. I mean, in fact, your textbook still has tables, right, at the back of the book. You know, that's what the normal table is, the t table is, and that kind of thing. but looking up tables is cumbersome, right? And then now you have fancier tools to do so, to do these things. So basically, an equivalent way to do this is called the inverse PDF, the inverse PDF, CDF. Okay. Alternatively, is exactly the inverse CDF. We can use stat software to look up the inverse CDF function of 1 minus alpha. Okay, so you understand what I mean. For example, if you can go on like R software or like Python, for example, and you look up the inverse CDF of the normal, standard normal at value 1 minus alpha. Why 1 minus alpha? Because the CDF, look at the probability that the distribution is less than, right? So less than being 1 minus alpha, right? So if you plug in 1 minus alpha, you just have to be careful to know what you're plugging in. But if you plug in the inverse CDF function at value 1 minus alpha, you will also get this, okay? So either way, it's not my point here to teach you how to do stat software. You learn that from other courses. The point being is these values right here, when we use them right in this class, they are constants, right? They're known values. So in other words, look at this, right? Constant, questionable, but constant because we assume no. So the only thing that's random, right, is here. This is the stat, right? This is the sample mean. But of course, right, you see the left point and the right point should depend on the sample somehow. If you construct a confidence interval that's completely constant, then something, or that does not depend on the sample, then something, right, awfully wrong is happening. So we'll explain why this is the confidence interval, right? 1 minus alpha confidence interval. But any questions so far? Okay, so let me ask you one question first, because there may be, right, misunderstanding about these issues that may be very simple. So let's say, right, given a, let's say given a normal sample, right? Let's say you have X bar to be 1.2. Okay. And let's say that you know that sigma equals to 1 for some reason. Then upon the above recipe, right? And, I believe Z.05 is 1.96. All right, I reserve my ignorance on this. Could be that, could be a little bit different. But anyway, right? So based on the above recipe, again, let's say n equals to 16 to make it nice, whatever, right? So based on the above recipe, you got something like what you're saying, right, is probability that the unknown mean, right, of this normal distribution that belongs to, right? So let's put that value in 1 minus 2 minus, right, sigma, sorry, Z alpha over 2, right? 1.96 times sigma over root n, right? Less than mu, less than 1.2 plus 1.96, 1 over 4 will be 0.05. Oh, sorry, 0.95, right? Because that's in between. Okay. So let me ask, what does this mean? Is this correct? Or, like, as you know, my favorite question in this class, does this make sense? Because if you don't understand what you mean when you write down these things, right, you get lost when you solve math. So this is some number, right? I don't want to calculate them out, but it's just a number. So you're saying that the probability that your unknown mu being in between these two numbers that you figure out is 95%. Is that right? That's what we mean by the confidence interval. Is that true? Yes or no? So let me ask you a alternative question. What do we say about the nature of mu or the nature of the parameters in this class? What do we say that our stand-in assumption for parameters in this class? So mu is assumed unknown, right? But a constant. Okay, that's our stand-in assumption. So if this is a constant, then it's either, you know, between these two numbers, or it's not, right? Like mu equals to 0, then it's in there. But if mu is like -10, then it's not in there. It's either or. How come this is a probability? What do we mean by 95%? 95% what? How do we explain that? Anyone know? So the point being, right, is that this is the wrong interpretation. Okay, I get it, and I'm putting it down here. But what I'm asking, right, is do you agree with me that mu is a constant? That's what we assume. Now, does it make sense to say this? Probability that -1 less than 0 less than 1 is equal to 95? I asked you this, right, because I know that you are exposed to a lot of concepts, but sometimes you must know what's right and what's wrong. If you just go around and you say, yeah, that makes sense, then no, our assumption of mu cannot be wrong, because how to say this, right? Assumption cannot be wrong. Either you are true to your assumption or you're not, right? You are faithful to your assumption, meaning that is my assumption. I just derive the consequence. Or you wishy-washy, it cannot be wrong or right. So here, right, the assumption is that. So what that means is this statement is wrong, okay? So like this, I hope you appreciate that this statement is wrong, right? This is very wrong. There's nothing that's probabilistic about this statement. So what's wrong with this statement? And again, right, that students tend to confuse these things a lot. But right, just because mu is unknown, right? So somehow you feel like, yeah, that means that the probability is in there, it's 95%, etc. That's not really the point. Okay. The point is that this statement is completely wrong because there's nothing random about this statement. There's nothing random about the statement. This statement is wrong. What we mean when we say probability, so on and so forth, like this, is pre-sample. Okay, like I said always before, that's the confusing thing about statistics in this course, that when we say something like this with upper big X, that's uppercase X, that's pre-sample. So what that means is before you form the sample, then you have 95% that the confidence interval you will form will contain the true mu. After you form it, then either mu is in it or not. Okay, so the above statement is a wrong interpretation. Or does not make sense. Okay. The right interpretation is that one way to think about it is this: if we conduct 100 experiments or 100 samples, okay, 100 independent normal samples, and construct 95, and construct 100 corresponding confidence intervals, then approximately 95 of them will contain the true mean. Is that okay? So in other words, right, if you have formed one confidence interval, then the true mu is either in it or not. But before you form that, okay, you can talk about, if I were to form one, then yes, 95% of the time, I have a chance of 95% of getting it. Or another way that kind of take the mystery out of it is, if you keep doing your experiment 100 times, then 95 of your confidence interval, 95 of your constructions will contain the true. Is that okay? It's very different from this kind of statement. And distinguishing the different meanings will help you to understand what we're doing. So if you want to be blunt, it's the difference between small x and big X. You're working with small x here, so there's no probability. Big X is a random variable. Small x is a constant. Question on this? Okay, so be very careful with this interpretation. And that's the meaning of confidence interval, all right? One single confidence interval, if you have formed it, is in or out. The probability, right, the 1 minus alpha, refers to the fact that if you keep doing this kind of activities, then 95% or whatever it is of the times, right, your confidence interval will catch the true mean. Okay. Same as what we did before too, right? When we say a parameter is a random variable, we don't mean that after you have done it, that is a random. After you have done it, is a constant. But before, right, before you do it, or if you keep repeating these experiments, then the law, the distribution, the sampling distribution that we state, right, will show if you keep repeating these experiments. Okay. Question on this? So let me show you, right, to bring home the point. We will work through this program and I show you. Here I simulate, right, normal with mean 1 and variance 4, right, standard deviation 2. And so I form the confidence interval in the case when sigma is known. And you see, for one thing, what does it mean to have the confidence interval being random? Here's what it means. That every time, right, I resample, I get a slightly different confidence interval. You see, they're kind of hovering around the same area, right? But they're different. Every time you form a confidence interval, it's different. And right, sometimes most of the time, right, this is 95%. Most of the time you catch the true value, which is 1. Some of the time you missed, right? Here you barely missed. You see that? But of course, here I only did 10 samples, right, to show you. Of course, if I do 100 samples, it's hard to see everything, right? Too much to print out. But you see here, right, the coverage rate, which is, of course, how many times I catch this, is 90%, right? If I run this experiment again, the whole thing, this time I have 100% coverage rate because every confidence interval I construct, right, contain the true mean, which is 1. Is that okay? So that's the meaning of confidence intervals. Every time you do it, you get a different confidence intervals. And out of these, right, roughly speaking, you have 9.5 times that will contain the true mean. But here, of course, everyone contains it. Chat. The infos generated aren't random, right? Depends on what you mean. After I have generated them, right? So what I mean is this: there's nothing random minus 0.11 and 2.37. That's a interval, right? That's fixed if you look at this. But of course, right, the next time I generate it, I don't know what the numbers will be. So in that sense, it's random, right? You see, each batch I generate will be completely different numbers. So in that sense, they're random. Okay. So it's the difference between realized value and random value. I keep telling you, right? If you roll a die, is it random or not? Before you roll it, it's random. After you roll it, it's 1 to 6, right? There's nothing random about it after you have rolled it. So it's just up to you to keep clear in mind what situation you're referring to. Is it okay? So yeah, it is always that difference between small x and big X that will confuse people. But you must understand and you must kind of distinguish these things. All right. Any question before we continue? All right. So 1 second. All right. So now let's go back to here, right? And notice this is big X. All right. And let's show that is the 1 minus alpha confidence interval. So back to the example, right? X bar plus minus z alpha over 2 sigma of root n, right, is a 1 minus alpha confidence interval. In other words, the probability that this is less than mu, less than x bar plus z alpha over 2 sigma of root n is equal to 1 minus alpha. Okay, I'll put a question mark here, meaning I need to verify it. Again, right, notice that I keep saying this, big X bar, okay, is a random variable. I did not form the confidence interval yet. Anyway, so the randomness, right, pay attention, the randomness falls on the X bar. Everything else is constant, okay? Everything else are deterministics. The only thing that random is here. So all right, this probabilistic statement is because of this. If you take it out, then there's no probability, all right? But anyway, so that means that everything centers around it. So you want to somehow put the, put the probabilistic statement on it. How to do so? Well, it's pretty straightforward, right? For example, let's take this statement. What does this mean? What this means this means is x bar minus mu, right, divided by sigma over root n is less than z alpha over 2, right? What this means is x bar minus mu divided by sigma over root n is bigger than minus z alpha over 2, right? So all in all, this statement is just probability that minus z alpha over 2 less than x bar minus mu divided by sigma over root n less than z alpha over 2, right? Again, still put a question mark, 1 minus alpha. But of course, right, you realize that this is where our sampling distribution of the sample mean comes in. If you have a normal sample, right, then x bar, the sample mean, exactly also has normal distribution with mean mu and variance sigma square over n. Therefore, right, this is just a standardization or the z transformation of the standard normal of the sample mean. So therefore, this exactly has the standard normal distribution, right? So of course, then, right, if you really care to draw out the picture, but I think everyone knows this. This is z alpha over 2. Because of symmetry, this is minus z alpha over 2, alpha over 2 here, alpha over 2 here, so exactly 1 minus alpha here. So this statement is now verified. Any question? We're good? All right. So that's an example, right? So, well, I guess to make it a little bit more dramatic, but future programs, right? What will I do? We just discussed confidence intervals for different types of parameters. Unfortunately, though, in this text and in chapter 11, it seems like most of them center around mu and sigma square, meaning population mean and population variance. Let me tell you, right, that confidence intervals are not just meant for these guys. Well, because, right, you see parameters play so many different roles in so many different distributions. Least of all, right, for example, the uniform, the parameters A and B, right? A definitely does not play the role of mu. B also does not play a role of sigma square, for example, right? A and B are population min and population max. So how to construct confidence interval for those, for A and B, for example, if you need to, right? So the danger of you learning confidence intervals from this book, or not from this book, they do try to teach you something. But in general, when you learn confidence intervals, you might fall into a formulaic thinking. That you're like, okay, I have this formula. Let me just throw it in and I get the confidence intervals, right? And you know, if anything, this class is not about formulaic thinking at all. And the point is this, that there are logics to this thing to begin with, all right? So, but somehow, because the pattern follows that way, then it just becomes like a formula thing for formulaic stuff, but for this and this only. So in general, right, we want to kind of understand the general idea about how to form a confidence interval. And let me tell you that in some sense, this is like, you know, unlimited, or not unlimited, but is a quite an advanced topic, because it depends on how you approach the distribution. there are many ways to form confidence intervals. All right, so I want to dispel you from the idea that confidence intervals is just a formula. But if we want to discuss the general ideas, then that's too much for this class. So what we will focus on is from the idea of a pivot statistics. Okay, basically you pivot around a statistics and you get your confidence interval. We'll discuss that. But there are many other approaches, all right, like from hypothesis testing or from likelihood function. We'll discuss this. And of course, we'll use this idea to explore things like this. What else do I want to say here for the confidence intervals? Confidence interval for different types, general idea about how to form a confidence interval. And, yeah, things to watch out for when forming a confidence interval. Okay. So probably these guys right here are worth discussing. This is like formulaic, and you see, right? We'll just walk through them very quickly. But so we will discuss maybe this first, and then this, and then this in some orders, throughout chapter 11. So let's do that 1, 2, and 3. Okay. So maybe let me start with 3 first. What do you want to watch out for? What does that even mean, right? When you form a confidence interval. So first, right, just generic things to keep in mind when you form confidence intervals is this. There is no unique confidence interval. Okay, even if you use the same approach, even within the same approach. I haven't discussed, right, what the approach is, so you probably don't understand what that means to begin with, what approach. But let's say you use the same pivotal statistic, you use the same pivot statistics, then you may not get the same confidence interval. Let me explain why. Very simple. For example, right, let's say that you have the x1 up to xn IID normal mu sigma square. And again, right, let's suppose sigma known. We have discussed, I hope, and it's convincing, that this is a 1 minus alpha confidence interval. But this also has a name. Actually, it's called two-sided. Okay. Symmetric. You may have heard of, right, one-sided confidence interval, or you might definitely have seen one-sided confidence interval. So the following also works. Minus infinity to x plus z alpha sigma over root n, sorry, x bar, and x bar minus z alpha sigma over root n. These are also 1 minus alpha confidence intervals. Now, of course, right, they are one-sided. And then, right, there's still one more, which is a little bit crazy, but it will be this. X bar minus, okay? Let's see what notation I want to use. Yeah, it's fine. Z P1 sigma of root n x bar plus Z P2 sigma of root n, where P1, P2 are given values. P1, you just require the P1 plus P2 equals to alpha. This is also two-sided, but non-symmetric. So I guess this is two-sided symmetric. All right. You know what this means, right? Same notation. ZP2 would be the, the value so that the probability that the normal curve is above it is P2, right? Whatever P2 is. So you see, This is symmetric because you use P1 equals to P2 equals to alpha over 2. So ZP1 equal to ZP2, right? But in general, you don't have to do that. So first of all, maybe a simple question. Do you see that these are all 1 minus alpha confidence intervals? For example, if I give you an exam question or whatever, a quiz, show that all of these are 1 minus alpha confidence intervals, then you can do it. Yes or no? I mean, be honest here, right? Because if no, then I'll show you some of these. If yes, I think if it's obvious to everyone, then I'll skip. I kind of hope it's semi-obvious. Okay, sure. Thank you, Christine. Any choice? All three may be too much. Maybe one or two. Any preference? Two meaning this one or this one? Okay, yeah, sure. So what are you saying, right? Notice by the infinity, all you're saying is probability that x bar minus z alpha sigma of root n less than mu is equal to 1 minus alpha with a question mark. Yes. So again, what are we talking about, right? X bar is the random part. So just isolate it. With the question mark. But do you see that this is obvious now? I claim that this is obvious. Why? What is this random variable? Correct. So this is standard normal. And exactly, right, is this picture where this is alpha. So this is 1 minus alpha. Is that clear? Same goes with this and this, right? Still, I mean, if you want, if it does not make sense, I do not, right? Assume so. I hope so. But if not, then you want to see some more, or this is enough? Is it okay to work for you to work out on these? Feel free to speak up. This is your chance. All good? All right. So, okay. So I want to say that do not take this as trivial. All right. They should be rather obvious, but if you don't see the whole mechanism and you want to work out these things for yourself, all right, it's very helpful. Trust me. All right. It's very helpful to work out for yourself on why each of these is 1 minus alpha. Okay. So you get the feel of it. But then, right, go back to my main point. My main point is that they are all 1 minus alpha confidence intervals. Okay, so why this or why that? Why do we go with this? Why not this, this, and this? So non-uniqueness, right, I hope is clear. In other words, you see, so here the pivotal, right, by the way, maybe let me clarify this. The pivot statistics, right, what is the pivot statistics? You see, all of these are playing around with the same random variable, this guy right here. So this right here is our pivot stat in this case. All right. So I hope that you see all four are playing around with the same random variable, just breaking it off at different points, right? This guy breaks it off at alpha over 2, alpha over 2. This guy breaks it off at alpha over 2 over here. Sorry, alpha below. This guy breaks it off at alpha above, and this guy breaks it off at P1, P2, something like that. Okay. So that's why I mean they all come from the same approach. But then, right, why the difference? Oh, maybe let's be more blunt. We use which when? Or are they all, same? We use them whenever we want, whichever we feel like. Do they have different flavors? Okay, so let me, if no one wants to guess, then let me tell you, right? They have different flavors to begin with, okay? So for example, and I won't go too much into this, but the following questions may be different for you, right? For example, suppose you ask this question, mu is not equal to 0, mu is bigger than 0, or mu is less than 0. I hope anyone will see that these are 3 different questions. Right? They're all related. They're all asking about the true mean, right? But they ask different kind of question, right? And by the way, right, this is hypothesis, right? We'll get there later, right? Right now, I just want to demonstrate that these are different questions. Now, again, you may have taken statistical courses that show you that you can use confidence intervals to answer hypothesis questions. So this clearly will be answered by the two-sided confidence intervals. This will be answered with the respective one-sided confidence intervals. Okay, and I'll leave it at that. This seems to be answered by the lower bounded confidence interval, and this will seem to be answered by the upper bounded confidence intervals. But I tend to get this mixed up, so I won't, try to write it down very clearly now. But the point being is, right, when you form this, what you have in mind is generically the 2 bounds for the mu. But when you form this, you have in mind the upper bound for mu. When you form this, you have in mind the lower bound for mu. Okay, that's the difference in the meaning, right? Because you see here, the minus infinity doesn't say anything. It just basically says that I don't care how low mu goes, but I want to know, right, with 95%, for example, how big mu can be. Right, same thing here. I don't care how big mu can be, but I want to know with 95% how low mu can be. All right. So they have different flavors. So depending on the questions of interest, right, some of these you pull out the right one to address that question. Okay, to begin with. So even though same confidence level, different flavors, different orientation. Okay, that's one thing. Any question on this? The second point, right, is, let's say then now between this and this. Yeah, go for it. This one right here. Yeah, all right. This is where I tend to get confused. One of them is associated with one confidence interval. But here's the thing, and this takes me beyond what I want to discuss now. But for example, right, when do you go with this? In other words, when do you reject the idea that mu is not equal to 0, is equal to 0, right? then you would go with this. For example, if 0 is not in this confidence interval, okay, it's like a negation, because this is 95% sure that this contains a true mean. So if 0 is not in here, then you would reject the idea that that the true mean is 0, right? So if you want, this is equal. So I think you go with the negation point. So here, I don't know. It seems like I would intuitively go with the lower bounded interval, but somehow, the question get flipped. So I don't know. But if you just use the face value of it, then right, this is minus infinity. This is upper bound. So just face value wise, this gives you an upper bound for me. All right. How it's connected to hypothesis testing is something else. I just drag this in to demonstrate that these are three different questions. That's all. I'm not trying to make the connection right now because I need to work it out more precisely than saying this, right? The point I want to make now is that, right, this deals with the two sides, but this only care about the upper bound for mu. As far as the content of the confidence interval goes, how you want to use it in a different question, you have to kind of modify. Is that okay? That's all I want to say. This is upper bound, this is lower bound, as clear as it gets in terms of confidence interval. Yeah. All right. The connection, I want to just drag it in to make my point, but I'm not making a connection right now in a precise way. I'm not. Okay. But all right. Any other question? The next point I want to make is between this and this. Okay. So this is two-sided. This is also two-sided. Then flavor-wise, they're the same. Then what's the difference between these two then? Flavor-wise, these are the same. So what's the difference between these two? Okay, good. But what does symmetry get us? It's beautiful, but sometimes you want it to be practical, right? Stat is more about practicality than being beautiful. So why symmetry? Wait, what do you mean by the lower one? You mean this or this? Oh, you mean when you take this out? Yeah, obviously, of course, because they're P1, P2. But together like this, there's still 1 minus alpha. Okay, because P1 plus P2 is equal to alpha. You want a proof for that? All right. So how does that work? Here, right? So I want to show that the probability that x bar minus zp1 sigma over root n less than mu less than x bar plus zp2 sigma over root n is equal to 1 minus alpha. Right? That's a question I want to consider. Well, again, right, all the randomness centers around x bar. So let me just convert them. So this will mean x bar minus mu over sigma over root n less than zp1. Okay. This means x bar minus mu over sigma over root n is bigger than minus zp2. Notice how the same pivot random variable shows up in all this proof. All right, again, that's why they're the same idea. It's this same random variable. So therefore, this statement is minus zp2 less than right? But then again, I claim this is obvious. Why? This is ZP1, right? By definition, P1 is above it. This is minus ZP2, right? But because the normal is symmetric, this means that P2 is below it. I want to capture the area in between, right? So what's the area in between? One minus P1 plus P2 in parentheses. But what's P1 plus P2? Alpha. Okay. So it is 1 minus alpha confidence interval. And it's two-sided. So, right, maybe my picture, my hand-drawn picture is not clear, but right, ZP1 and minus ZP2 are not symmetric. Is that okay? All right, cool. So then the question is, right, I guess you see the different flavors here, right? Two-sided, one-sided upper bound, one-sided lower bound. But these are both two-sided. What's going on here? Anything different about these two? Why do I want to use a symmetric one? Or if I feel like it, can I split that into, right? I don't know, let's say 95%, right? 0.1 here and 0.4 there. Why not? Any idea? Okay, so the first thing you want to care about confidence intervals, right, is probably flavors, or frankly speaking, right, what kind of orientation you want. But the second one you want to care about, and this is not too emphasized because it probably is a little more advanced topic, and it's already baked into the standard ones, but the length of the confidence intervals is also a topic that people pay attention to. Because, for example, right, if you have two confidence interval 1, let's say, right, and confidence interval 2, they're both 1 minus alpha, but the length, right, the length of 1 is less than the length of 2. And suppose they have the same flavor, then which one do you prefer? You prefer the larger one? you're not quite putting yourself in that context, right? Because what do you want? You want, yeah, I think I know why you do that. But notice, right, the amazing thing is both of these catch your true mu with the same confidence, meaning they both catch. Yes, no, it's fine, right? But of course, humanly, right, you want the larger one to catch it more. But the point is this, right? Here, the larger one doesn't do anything more for you because it's already constructed to be 95%, both of them, okay? So that's the thing, right? That's the subtle thing. You would prefer this. You would prefer the smaller one if all else being equal. All else being equal, all right? Of course, if you fix the same approach, then the larger one will catch more. But sometimes, right, different fissioning gives you the same coverage rate, but with different lengths, all right? For example, it may seem amazing to you or not, but the length of this symmetric one is always shorter than the length of the non-symmetric. Okay, so when we do this, it's not just out of beauty, aesthetics consideration. This is the shortest one among all possible choices of the symmetric of the two-sided confidence intervals. Okay, this is the shortest one. You see why? Actually, that would be an unfair question. That would be hard. Not hard, but that you need to sit down and think about it. So you will have the pleasure of thinking about it for this week's quiz. All right. In the quiz of this week, I'll ask you to show why that is true, with some guidance, of course. But yeah, the point is that this is the shortest one. Okay. Among the two-sided. Any questions? Okay, so those are the things that we want to keep in mind when we form confidence intervals. All right. I mentioned this because, you know, for better or for worse, these points tend to be swept under the rug when you kind of are into a complex problems. You just try to form something. You don't even look at like the length, or you don't even look at the orientation. But when you take a step back, these things are things that help you evaluate the confidence intervals, all right, to kind of bring you down to earth. So they are always in the background that if you keep them in mind, it helps you understand what you're doing more. All right, questions? So let's go back to point 2 then, about the pivot stat. And I think depends on, I don't know if there's a universal name for this, but if you look up some resources, I think they would refer to this type of confidence intervals as pivotal confidence intervals. The point is that, right, the idea is you pivot around a stat to form a confidence interval. Okay. For those of you who, I understand that, like English is not our first language, pivot may be a strange name, but pivot just means turning around, screwing, like, so basically you use it to turn things, to crank things out, right? That's pivot around means you just turn around it. So for example, okay, x bar minus mu over sigma of root n is our pivot stat for mu in the previous example. Okay. How do we pivot? Well, the idea is simple. You need something now. First, you need to know the precise distribution of the pivot stat. Okay. So this is where, like, our work in chapter 7, chapter 8 comes in, the sampling distributions, right? We skipped over something like the T and the F, but those are exactly kind of used to work on the pivot stat, or they are also referred to as test stat in some way. But test statistics is more in the context of hypothesis testing. But confidence intervals and hypothesis testing are very closely connected. So, it's the same thing. It's not surprising that they're the same things. But this is why chapter 8 is relevant. That's all, right? And the common ones, meaning the common distribution that you will discover your pivot stat to be, are standard normal, T, F, and chi-square. Okay, and that's why you keep hearing things like the t-test, the chi-square test, the f-test. You don't hear the standard normal test too often. The reason is, right, the standard normal assumes something very unreasonable. That is the, the sample variance, sorry, the population variance is known. But technically speaking, right, any of these guys carry with them their own test, their own confidence intervals. Okay. Let me say one small observation. Okay, maybe not. Let me do this. Let me do step B, and then I'll show you. Step B is actually just from step A. From A, you know the precise distribution of the pivot stat. In this case, for example, you know it precisely that it's standard norm. Then the step B is you just write down a probabilistic statement using A and the corresponding quantiles. And then start rearranging the statement to isolate the unknown parameter. Okay. So it's like a mouthful, but what is this, right? So write down the probabilistic statement using A and the corresponding quantiles. What do I mean by this? So let's take this and see what it means. Well, so my pivot stat is x bar minus mu over sigma over root n. I know exactly its standard normal. So therefore, right, if my target is 1 minus alpha, that's a confidence level, then I just need to make some statement that has 1 minus alpha probability. That's what I mean by write down a probabilistic statement using A and the corresponding quantiles. Why corresponding quantiles? Because I know my target is 1 minus alpha. Therefore, I need to put something in here less than, bigger than, whatever, that somehow achieve 1 minus alpha. And therefore, you see, right, the most general statement I can make here is ZP1 minus ZP2. Do you see? So this is the probabilistic statement I can make. All right. So it's sort of the reverse of what I just showed you before. What I showed you before was, right, from to prove that the confidence intervals work, you just chase it back to some kind of pivot random variable. So this is the easy direction, because in some way what the pivot is given to you. The forward direction, right, how to find the confidence intervals is supposedly harder, because in real life, in a new experiment, no one will tell you what the pivot random variable is. 90% of the job is to find that pivot random variable. Okay, but of course, like in the class like this, A is usually given to you in some way. You have to work on B, because I mean B is supposed to be easy, but you need experience. But 90% of the work in research or whatever, right, in a new question, is to find on A. All right, but once you have that, right, then you just kind of write down some distribution that you want, some probabilistic statement that you want. It's very flexible, and that's why it's not unique. Depends on how you structure this. You get different types of confidence interval. But that's this part. And then start rearranging. Okay, start rearranging. That's the pivot part. That's the act of rearranging is exactly the act of pivoting, right? Because here, right, what do you want? You want confidence interval for mu, right? So you want to isolate mu now. You want to isolate mu, right? So before you want to isolate the randomness to calculate the probability. Now you know the probability, but you don't know the confidence interval. So you want to isolate mu. So right, to isolate the unknown parameters. Sorry, not S, right? A parameter, yeah, without S. So it's just mu. So in other words, right, mu is unknown, so I need to isolate it. So again, you see it's very familiar. Work with this. You get X bar. Sorry, not X bar, right? I want mu. So I want mu, so mu here will be bigger than X bar minus ZP1 sigma over root n, right? And working with this gives me mu is less than X bar plus ZP2 sigma over root n, right? And it just so happens that if you plug these two together, you got probability that X bar minus ZP1 sigma over root n less than mu less than X bar plus ZP2 sigma over root n is 1 minus alpha. And voila, right? That's your left point, and that's your right point. Is that okay? And now you see, right, the flexibility, or here, you just form some kind of probabilistic statement, probabilistic statement. And so you see, right, if you choose P1 equals to P2 equals to alpha over 2, then you got the two-sided symmetric. If you choose P2 to be 0, right, then that means ZP2 is, if you choose P2 equal to 0, then what's the ZP2? Here's a curve, right? P2 is the one above. But if you want that to be 0, then what's P2? What's ZP2? Infinity, right? And so of course here, P1 will be alpha. So that's the one-sided lower. And of course, right, the other way, P1 equal to 0, P2 equals to alpha is one-sided upper. Is that okay? But you see, it all comes from the probabilistic statement involving the pivot random variable. That's it. The rest are just algebra. The rest are just algebra. Any question? Okay. So this brings me up maybe to the next point. So this is capturing, right, the pivot random variable technique. All right. And this will be the way I will present it for all the random variables. For all the confidence intervals that we'll encounter later. But one thing that's very important, right, for pivot random variable, for pivot random variable is this. We require, right, that the pivot random variable can only depend on the current parameter that we are forming confidence interval for, and nothing else. Okay. So in other words, what I'm trying to say is this. I mean, when you form a pivot random variable, right? Because you will pivot around it, whatever it depends on, right? So basically you isolate this guy. That's your unknown one. You want to form the confidence interval for it. You see, everything else will appear right in the right and the left point. Will appear in the boundary of the confidence intervals. So this guy, right, the pivot random variable must depend on it, by the way, right? It must depend on it. Otherwise, what are you forming confidence interval for? But on the other hand, if it depends on something else that does not make sense, in other words, you don't know the value, then when you form the confidence interval, your confidence interval will also not make sense. Okay. So in other words, suppose a sigma is unknown here. If sigma is unknown, then this would not be a legit pivot random variable. Is that okay? Here is fine because we assume sigma is known. So there's nothing else that would violate any assumption. But so for example, right, if sigma is unknown, then x bar minus mu over sigma of root n is not an acceptable pivot random variable. Is that okay? So that exactly right following this observation. Any question? So, but exactly, right? What do you do in this case? Because that is the case, right? That is of most interest to us. That if sigma is unknown, what do we do? Because again, right, that's the practical thing. So obviously, right, intuitively, right, the intuitive thing to do is to replace sigma with its estimator. And you see why now estimator makes sense, or estimator is relevant. Because like your exam, right, like the midterm one, anytime you encounter a random variable that is unknown and you need to use it somehow, then the most sensible thing to do is just to plug in, right? It's called a plug-in approach, which is kind of like a funny name, but basically you just plug in the estimator to the unknown parameters that you need to use, right? So here sigma is unknown, mu is of interest, so you of course you don't replace with anything, but sigma is unknown, so you replace with s, right? The estimator. So s is the sample variance, s squared sample variance. So this is sample standard deviation. But of course, right now, what do? That now you go back to square one, meaning you need to know the precise distribution of previous stat, because now your previous stat is different, right? This is random. This is random. This is no longer a standard normal. So you need to know its exact distribution. Okay. So you have a new previous stat. You need to know its distribution. And then once you know its distribution, then you play the same game again. You write down something like this, but with S, right? And with the quantiles. But what is it? And so I save you the suspense, right? Because I guess you know what it is. It turns out, right, that this has the T n minus 1 distribution. Okay. And that will take us back to our chapter 8, right? to learn about this t distribution. Okay, and so this is where the appropriateness of studying what this distribution is about is there. So I said we skipped it and we'll come back, right? So this is the time to come back. And the motivation is exactly to form the confidence interval, right, for the mean of a normal distribution when the sample variance or the sample, also when the population variance is not known. Okay, so good place to stop here. We will pick it up next time. All right. Any question, then I'll answer. Otherwise, have a good weekend. I'll see you next week. Thank you. You too.
Professor?
Yep.
I actually had a question about when we were working on the length of the confidence interval, you said that, yeah, and this is purely about the notation that we were using. So this is, so you said the length of confidence interval 1 is less than confidence interval 2. I was just wondering how you numbered 1 and 2. Yeah, this one right here.
Whatever you want. For example, right?
Mhm.
One in my mind here is this guy, and 2 will be this guy.
Oh, okay. So 2 was the two-sided asymmetric. Okay.
I mean, the key is the same flavor, right? But suppose that you don't care for the flavor, you can still compare the length of this and this. And guess what? Actually, the length of this is still less than the length of this, actually. Okay. But so lengthwise, this is the most preferred one. But I do not want to say that this is preferred to this overall, because this is a little bit special. This is upper-sided. So you use it for a different reason, right? So it's like compare apples and oranges. But comparing this and this is, to me, comparing apples with apples. But yeah, I mean, if you really just ignore the flavor and compare length, right? So 1 and 2 that I refer to can be anything, right? Two confidence intervals. 1 and 2 I refer to only requires that they have the same coverage rate, which is 1 minus alpha. Then, of course, right, given the two, I mean, to be blunt, for example, suppose you have 2 insurance that gives you the same coverage. Will you go for the more expensive one or the cheaper one?
But you go for the cheaper, yeah. You go for the cheaper one.
Right.
Yeah.
Whichever insurance it is, right? So there you go, right? Whichever confidence interval that is, right? As long as they have the same coverage, you go for the shorter one. That's all I'm trying to say. The harder thing to show now, right, is in this particular construction, then this guy achieves the shortest shortest length. Why? That's the question, right? But I mean, like philosophically, right, same coverage going for the shorter one, I don't think that needs any argument.
Right. Okay. Yeah. This definitely makes a lot more sense, because you said that regardless of what the choice for confidence interval 2 is, it'll always, the length of that will always be greater than the than our notation for two-sided symmetric for number 1, basically.
Yeah. But 1 and 2 that I mentioned here has no special meaning, right? It's just 1 whatever and 2 whatever. It's just basically somehow the first one is shorter length.
Right. Yeah. And it's the same coverage basically, but it's just,
that's the key, because of course if you have the longer one with higher coverage, then who are you to say that one is worse? It has higher coverage, right?
So in that case, how would you make your choice of?
No, then there's no choice, because actually then what do you want with the coverage? For example, right, if I reduce the alpha, then I will make this larger, right? I mean, it's just a basic fact of life that the 99% confidence interval must be bigger than a 95% confidence.
Right. Yeah.
Then you say that you prefer the 99 over 95? I mean, right? I mean, it's 99, but it costs you more because you have.
Right. Yeah.
Yes. But of course, sometimes people prefer 99 because they want the 99% confidence. It's not because they prefer 99 because 99 is large. You understand the difference?
Yeah, I understand. Yeah.
Anything else?
That's about it, Professor. So thanks so much. Thank you.
Sure. All right. I'll see you then.